Hello everyone, I'm Nivedita from third year CSE department studying in SVCE. My topic for today is generating opcode using SIC machine architecture. SIC is abbreviated as Simplified Instructional Computer, and for XE is extra expensive or extra equipment. SIC mission architecture consists of the features like memory, registers, data formats, instruction formats, addressing modes, instruction set, input, and the output. Registers like SIC architecture consists of five registers. In addition to those, in this SIC architecture, it consists of B, S, T, and F registers are provided by SIC in addition to the registers of SIC. When it comes to the memory, maximum memory available on a SIC system is 1 megabyte, which means 20 bytes. The mnemonic number and special use for these registers like BSTF is 3456 and base register, general working register, floating point accumulator respectively. Data formats SIC provides the same data formats as the standard version. In addition, there is a 48-bit floating point data type. The fraction has a value between 0 and 1. The assumed binary point is immediately before the I order bit. For normalized floating point numbers, the I order bit of the fraction must be 1. The exponent as unsigned binary number between 0 and 2047. Floating, the sign of the floating point number is indicated by the value of S. 0 is for positive, 1 is for negative. A value of 0 is represented by setting all bits to 0. Instruction formats SIC provides some instructions that do not refer memory. There are four instructions. They are format 1, format 2, format 3, and format 4. Format 1 consists of the 1 byte which contains only operational code. Format 2 consists of it is 2 bytes, that is 16 bits. First 8 bits for opcode, next 4 for register 1, and the following 4 for register 2. The number for the registers go according to the numbers indicated at the register section. Format 3, first 6 bits contains opcode, next 6 bits contains flags, last 12 bits contains displacements for the address of the operand. In this format, 3 is recognized by the E value. If E value is set to 0, then it is considered as the format 3. Format 4, same as format 3, with an extra X digits for addresses that require more than 12 bits to be represented. In case of the format 4, it is recognized when E value is set to be 1. Instruction formats, like there were the instructions along with the examples. For format 1, it is ASAP. For format 2, it is add RST. For format 3, it is LDA ASTRI. And for the format 4 plus J sub RD rec. Addressing modes and the flag bits, when it comes to the modes, it have two modes, that is base relative and program counter relative. And base relative is indicated by b is equals to 1 and p is equals to 0, and target address calculation is base relative plus displacement. And when it comes to the program counter relative mode, it is indicated by b is equals to 0 and p is equals to 1. Target address is calculated by program counter plus displacement. SIC machine architecture consists of the addressing modes and the flag bits. There were some addressing modes like base relative, program counter relative, direct, immediate, indirect, index, extended, and all. For all those things, particular flag bits were mentioned. When it comes to the SIC machine architecture problem, here it is the instructions and the three columns like labels, opcode, and operand is given. We need to calculate the log CTR and the object code for this particular problem. Like here we will discuss first how to assign the location counter for each and every instructions. So the first location instructions location counter is always equivalent to the value mentioned in this particular operand field, that is 405D. So 405D I will assign it for the first instruction. uh, Now if we want to calculate the location counter for the section, you have to check what is the type of the instruction it is, whether it is type 1 or type 2, 3 or 4. If it is 1, we have to add 1 byte. If it is 2, 2 byte, 3, 3 byte, 4, 5 byte. If it is yeah, next instructions. Now, one thing you need to remember, if there is a register involved in the instruction, it is type 2. If it is a plus is written before the instruction opcode, then it is type 4. Otherwise, it will be type 3. So in this case, X is present. X is nothing but a register. So so it is type 2. In case we'll add to this one. So this is 405D first of all, 405D. So this particular thing we will add to, we will get 405F. That is the location counter for the next instruction. This is type 3, as I said earlier, because this particular instruction does not involve a register, as well as there is no plus here. The same thing goes with this one, same this goes with LDCH, and the same thing goes with all the instructions in this particular case. TIXIR register, so this is type 2 case. So we will start with the locations, like if it is type 3, then add 3 bits and goes on. So when we comes to the opcode for the clear X, as this is format to 2, it consists of the opcode and the register 1 and the register 2. Here for the clear, it is mentioned that it is B4. So we'll take that it will take the successive bits, not success, sorry, significant bits, and it will take the significant bits to the opcode. So as this is 8 bits for the opcode, it is taken as 8 bits, and first register, that is X value, is 1. So register 1 takes 1 value, so R2 register takes 0 value. So for the clear X, the opcode is B410. When we goes to opcode for the LDT length, this is a third type instruction. First tip are the 6 bits are the opcode. NIX BPE is for indirect addressing mode. I is immediate. X is index addressing mode. B for base relative. P for program counter relative addressing mode is set to 0 because it is a type 3 instruction. If it is type 4, we would set to 1 year. Now we need to calculate the displacement. If it is type 3, if it is type 4, we'll get 20 bits address here. Yeah. We need to calculate the displacement here. Here, the LDT is 74. So LDT is written in binary format. The first significant bits we need to take here. So that is nothing but the opcode. In this case, we don't have hash or something else. So this is neither immediate nor immediate. So we'll write 1 year, and E is set to 0 because it is format 3. So we have to detect this is base relative or program relative. So we need to calculate displacement. So we'll take displacement is equals to the value of the length. We don't have the value of the length here, but it is given in the problem, that is 4036 minus the PC value of the address of the next instruction, that is 4062, that is minus 2C. This cannot be written like that, so it has to be converted into the hexadecimal value and it has to be written, and this one's object code is 772FD4. And next comes the TD output. Here for the TD, it is written the object code, where in the same way where we want to take some significant bits, then we want to calculate displacement, and program relative, we want to check if the values comes between these values, then we will consider it is the base relative or program relative, and we'll write the opcode for the third one. Like opcode will continue for all the things, as we'll see, as I show for JE Q, W loop, this is for LGCH buffer X, for WPD output, for TIXRT, for JLT loop, for RSub, and this is the object program. First, we'll look into the object code for all the things in this table. This is called the object code for all the things in this table. Where object code is calculated by using those diagrams using opcode and the flag bits. And after calculating all the object codes using this, we need to calculate the object program. This object code consists of the three things, that is head section, text section, and the what is it, end section. So, header section starts with H. The next six columns are used to represent the name of the particular program. In this case, W or REC. We will write in the first five columns. Sixth column is empty in this case. And then the next six columns are used to represent the starting address of this particular program. In this case, it is 405D. Like we have written 00405D because we need to write this particular thing into six columns over here. Here, coming back to the next four columns, the four columns are used to represent the length of this particular program. The length of this particular program is 4077 minus 405D here. That is equals to 001A. The next section is a text section. Text section can be one or more based on the number of bits given. In this case, we can notice that it is only one text session. Each and every text session consists of 69 columns. So first columns is T, and next columns are used to calculate the starting address, and next used to calculate the length of this particular text record. So there are totally 9 columns. Remaining 60 columns are used to represent the object code over here. If it is more than 16 columns over here, we have to create one more text record and so on. Here I have started writing all the text records here. They will fall into 60 columns. I have written everything here. You can see here. First one is B410, second one is 772FD4 and so on. Everything I have written here. Now if you go on counting the number of columns here 4, 6, 10, plus 6 16 plus 6 22 plus 6 28 plus 6 34 plus 4 38 plus 6 44 plus 6 50 plus 252. So total number of columns are 52. And one more very important thing is 2 columns is equivalent to 1 byte. So 52 columns is equivalent to, so we'll do one thing, 52 columns are divided by 2, so it is 26. So 26 bytes, we will convert it into hexadecimal number, we will get 1A. This is what written in this length, but we'll write it here. And the last part of this object program is end record. It will start with E, and length of this particular is the starting address of the program, that is 00450D. This is the final object code, how it looks like for this object program. Thank you.